SQL. E-business suite is such a crap. Yeah, not only, but
Any system which lives for 30 years.
yeah.
It's okay.
Could be worse. Have you ever worked with people?
No, but I can understand what's happening. So
Same bullshit.
Hello everybody, thank you all for showing up. I hope everybody read this safe harbor statement. I will be diving into the inner workings of the database, and actually the second slide says most of the time parsing will probably not be a problem. However, there isn't a lot of documentation about what the Oracle database actually does, and most of the stuff that I found is either really confusing or plain wrong. So how can you tell whether you've got a parsing problem or not if you can't tell because there isn't any really concrete documentation about it? Let's time it. I will not take questions during the talk because I just have way too much information. I don't even know how far I will come. So I will just do the talk. If you have any questions, type them in reminders on your phone or something like that, and ask me afterwards. Then I'll try to explain to you as good as I can. I don't know everything. This is all that I'm presenting is based upon my own research. So there is even a chance that I'm just plain wrong, and that is why in the previous session also, if you want to rely on something which is said here, I hope I give you enough information to prove it to yourself first. That's really important. This is all based upon a single version. I used version 18.4 to do my research, and there is a chance that this will be different in another PSU even. Because this all is hardly documented, and as you will see, the documentation conflicts itself sometimes, which I will show, and it can change. Although, based upon my research and looking into the inner working of the database, essentially since Oracle 10 or something like that, my experience is that things do not really change that drastically. It can, and it happens, absolutely, but on the other hand, most of the stuff stays in place. So if you gain some knowledge about inner workings, you can prove to yourself that it's still working that way, and see if it's true. So that means that despite the fact that everything can change, I think the gaining an understanding of this is still very useful. These are statements from Docs OracleCon, and because I first tried to understand what Oracle defines as parsing, my conclusion is Oracle doesn't have a definitive statement about parsing, unless somebody has some documentation which is really conclusive. But if you look at the first one, SQL processing says the stages of parsing, optimization, etc. So that to me means that optimization is something different than parsing. And then Pascal says that it's preparing, and it includes it more or less. So that's really conflicting. And other statements, for example, one of the questions I try to answer for myself, which hopefully I can answer to you too, is what is a hard pass and what is a soft pass? But if Oracle says hard pass is to build an executable version of the application code, which is mostly true, but then saying a soft pass, any pass that's not a hard pass, it's not really helpful to get an understanding. And another stuff. This picture is the picture that a lot of people use to tell other people and to document how Oracle works. And I think this diagram is the most confusing diagram ever, because the dotted square, I think Oracle tries to tell you that that is parsing, but that would mean that hard pass is outside of parsing, right? It's plain logic. And it says then that a soft pass is doing a syntax check, semantic check, and a shared pool check, and then execution. And I don't understand. I don't understand this. So let's see how this really works. The first thing is, anything that you execute against the database is passed, and Oracle tries to execute it, if it can. And this includes invalid SQL. Why? I didn't even know this before I before I did this investigation. And one of the things that this might be a bit obfuscated for you is SQL Plus keeps you from executing really weird stuff against the database, and it will stop you doing it. However, if you create a Java program, you can execute anything you like against a database, even if it doesn't make sense at all. And for example, in this case, I tried executing x, which of course doesn't make any sense. And it then will throw an ORA 900. If you like to try this for yourself, this is the Java program. I will make the slides available so you can try that for yourself. And then, look, wait a minute. If I try to prove that to myself, if I search for a SQL text like XX, Z, it says now there is nothing like that. However, it just filters out the invalid objects. If you look in $KGL cursor, and you will find two entries, and one entry which has the same handle address as the parent address is the parent, and the other one is the child. And then we will go into that further. I had first a big diagram about a logical representation of several library case objects, and my colleague said it might be better not to have the full picture all at once because it's kind of abstract. So I try now to go in steps. The library cache is, you find objects in the library cache by using a hash bucket, and a hash bucket is a memory area where the database, any object will get an MD5 sum of the name of the object, and then using probably, I have to look into that, the last 8 characters of the MD5 sum, which is the SQL ID you see, it will hash it over the hash buckets. And in that way, any other session which tries to find that object can use a simple computation to directly go to the bucket in which a certain handle in the library cache should exist. And if it isn't there, it will create it. So in buckets there are 0. The first bucket, so that's the blue square, contains nothing. That's an empty bucket. The second bucket has 2 parent handles. If the MD5 checks them, if the last 8 characters are the same for multiple objects, the database will link the handles together. So in the bucket there is a pointer to the first handle, and in the first handle there is a pointer to the second handle. And the fourth contains only one handle. And maybe I should have known it, but I didn't realize it. The library cache does not only contain SQL and PL SQL. The fourth one, a SQL area cursor, that is a SQL or can be a PL SQL object. But it also contains, for example, the top one, the top handle, is a table, procedure table. So that is a library cache representation of a table. And there's also something like, which is called SQL area build, and something which is called SQL area stats. And SQL area stats is actually an object which holds the statistics which you can see in VDollar SQL area, where it says there is this much time spent on cluster, this much time spent on I/O weights, etc. That is what that object is. And then handles, the different types of handles can have additional memory areas called heaps allocated to it. And for example, a SQL area build object doesn't have an additional area, just the handle is enough to do its function. The top one is the table procedure has a heap 0 and a KGLS heap. Um, and actually the X's you see are the last 8 characters of the hash of the object. And then a cursor, a SQL cursor looks like this. And that is, the first one is KGLNA, and A means name. And I put a dotted line with an arrow, and that line is there. If the text is too big, it will allocate an extra memory area called KGLNA, and then put the text there. But most of the cursors have small enough text that it will fit inside the handle. And then every cursor always has a heap 0, and the heap 0 just contains a table of childs. The parent cannot execute anything. The only way to execute something is using the child. So any cursor must have a child cursor before you can execute anything. And then the child cursor has a KGL H0, heap 0, which is the exact same name as the parent. And the X's are the same because anything inside an object has the same hash value, of course, because it's all concerning the SQL, in this case, for the SQL. So these two allocations, for one is a child and the other is a parent, have exactly the same name, and that is confusing. And then you've got SQL A, and SQL A means SQL area, and this is also known as heap 6, and heap 6 contains your execution plan. In the old days, you had to do an explain plan for a statement to obtain the execution plan. Nowadays, the full execution plan is stored, as far as I'm aware, in heap 6, so you can just obtain it directly. You don't have to execute it. And it contains other runtime information for the database to be able to execute the SQL. So this is how that looks like. Can I see this myself? Yes, that's actually really easy to do, and this is what I've been doing for quite some time for the research of this presentation. Just all the session set events, immediate trace and library cache level, and in this case 16. The 16 means the contents including dependencies and children. And this is how it looks like. It's a lot of text, and what is most notably is the top line says bucket, that is the bucket, and a bucket contains a mutex. It has mutex behind it. The library cache handle contains the hash value, that is the 8-character hash value. The object name is the name of the SQL statement, and then the full hash value is the full MD5 sum of the SQL text. And if you look at the last 8 characters, these are the same as the hash that you see 2 lines above. What is notable here is there are counters, so there is counters over there, and concurrency shows you 2 mutexes here too. So now let's look what actually happens when SQL is parsed, and this is a hard parse. A new statement is introduced to the database. Can I see this for myself? Well, sadly there is no nice Oracle trace which will just show you this. The only thing there is what I did, is using pin tools and look at the C functions and then try to derive the function of what a C function actually do. Luckily, the C functions most of the time have really descriptive names. So it's fairly easy to guess what they do. So I will take you through it, what actually happens when you hard parse a statement. I execute the select count from test. You'll see why this matters. So, the first thing the database does is generate a hash value from the SQL text in this case of a cursor. Then the session cursor cache is inspected. That is what you said using session cache cursors. It tries to find the hash value because it's stored there. Sometimes there are function names behind it, and if the function names are behind it, it's a unique function, so you can actually identify this action happening there. Certain other functions, like for example, a lot of mutexes are obtained. I've counted them. Well, I've actually got a spreadsheet of a hard parse, and it has more than 200 mutex gets, which constantly use the same function. So it doesn't make sense to put these there because they don't mean anything. It's constantly the same function. Okay, so now the session cursor cache is inspected, and because we're doing a hard parse of a new statement, and there is nothing in the SQL area, nothing is found. What it then does, it looks up the parent handle via the hash bucket. And because it's a new statement, it creates the handle. The handle needs to be created. If a handle, no, the handle is created. After the handle is created, it will lock the handle. And this lock is not an enqueue lock, like you know from Fedora lock, like the TM lock, TX lock, etc. This is what is called a breakable parse lock, and that's actually just a state in the handle. And in order to make that change to the handle, to lock the handle, it needs to take a mutex. So that's where a mutex will be taken. After the handle is locked, the handle is pinned, and when the handle is pinned, it will create, if there is a heap 0, it will create a heap 0. It then unpins it, and because we then got a heap 0, next thing it does, it searches for a compatible child in the child list in heap 0. Because this is a new statement and we've just created it, obviously there is nothing. So then it is going to build the child handle. In order to build a child handle, the first thing it does is it creates a $build $, and then the last 16 characters of the hash value, and creates an independent object of that, which is the SQL area build object, which I just showed. And it will look it up whether that exists. Of course, this is a new statement, so it doesn't exist, and it will KGL lock it. So that handle is then locked. That's an independent handle, but then it creates the child handle and it KGL locks the child handle, and then an enqueue is obtained. And I didn't even know that this enqueue existed. I've looked it up. You can see the enqueue names, and apparently the CU enqueue is for bind variables, but we're not looking, this is a statement without bind variables, so I'm not going into this any deeper. And then the child handle is pinned, and pinning, as I said, creates the memory area. It is important, and nowadays the shared pool is way better, but if you need to create a new heap 0, there needs to be memory obtained from the shared pool in order to allocate the heap. In order to do that, it needs to get a shared pool edge. And this is what causes, which could cause contention, because it's way better than in the old days where you only had a single shared pool edge, but still, even despite the segmentation of the SCA and the shared pool, it can be costly. So that is why you should cache cursors and try to reuse existing cursors. And it then creates a SQL area stats independent object, so that's yet another object, and it follows the same principle. It looks up the hash value of this SQL area stats object, it can't find it, so it creates it, then it KGL pins it, which creates the heap 0, that's the allocate, and it then unpins and unlocks the object exists. And then it unpins the child handle. Then we start doing the initialization. We just allocated stuff, the initialization of the child cursor. And that is a function key as parse child cursor. And heap 6 is allocated because that's where the runtime information for the Oracle database to actually execute the SQL. So now we're going to page 2 of what it all has been done. Once we start to initialize the child, we are doing the syntax check. And if you remember the schema from the Oracle documentation, which said the first thing is what is done is a syntax check, then a semantics check, and then we're going to see if it's in shared memory. That's not true. That's only when the child is actually initialized and created, it does a syntax check. After the syntax check, it does a semantic check in OPSM, and it will validate all the dependent objects. And in order to validate the objects, I think by now most of you will get it. What it does is it will get the hash value for the object, it will look up the bucket, and then it will get it and pin it. And what is important here to realize is that it will, once it pins the object, it adds it as it adds itself as a reference to the object for the dependent object. So in the remote object, it will add itself as a dependency, and it will add the table as a dependency. So it's on two places. Obviously, this needs a mutex get. So that is really important to realize. But the remote object, the object, for example, if you do a select on a table, the table object will have a reference to your SQL. So a table knows exactly which SQLs all are executed or still exist on inside its dependencies list. And this is also how, when you remove something, it's really easy for Oracle to determine what needs to be invalidated, because there is a complete list, always. Then it validates authorization, and that requires a SQL which looks it up in a table called obj_auth$, and it looks up authorization. And that is the reason why I execute a dummy SQL if I'm going to look in the functions, because it needs to create this cursor to look it up first too, because it's a plain SQL which is executed recursively. And then the child cursor object information for execution. So the ability to do the execution, all the information for that is stored in heap 6. Then access path analysis is done, and this is effectively optimization. So after all this, now it knows what to do. It has the basic information of what it wants to do, and then it starts doing access path analysis. In traces, you see access path analysis and cost-based optimization being two different things. What I see when I look at the backtrace of all the C functions is any optimization happens in a function called APA-DRV, which to me means access path analysis driver. It then creates yet another object, which is called optimizer directive owner, and we're not using optimizer directives, but still it creates this object, and you know the path, right? And then the costing of the access path and all the transformations which it could do is done. And then it starts creating the actual query structures, which is in heap 6, which is needed for execution, which is done in QKA DRV and QKA DRV2. Also at that time, the actual explained plan is created and put in heap 6, so you can obtain it directly. And annotations around it are there. Then it does auditing. Well, I see a function auth pray, and I see functions as child of it, which do auditing, but I haven't looked into it further how that works. And then this part is done, and it then stops. What it then does is, all the dependent objects which it needed were pinned. And any object which you're working on needs to be pinned to indicate that nobody else can just remove the object and throw it away because it needs memory, for example. So all these objects were pinned, so these are all unpinned. The CU enq, which I just talked about, is freed. And then the child cursor is added as a child to the parent's heap 0 in the table of childs. And as a last part, the $build, hash value object is unlocked. So these are all the functions which are executed that I can see in version 18.4 for hard parsing a new object. That's a lot of work, and but parsing again should take advantage of it, right? So this is a long list of all the stuff which I just talked about, and this is the first parse of a statement which is not in the library case. Doing a second one only executes these, and there is a specialty between the second and the third. The second one still validates authorization, and the third execution does not need to do that because it's still cached. After the fourth time of executing manually SQL, it's just picks up the hash value, and then inspects the session cursor cache. The session cursor cache got a link, a pointer to the parent handle, but also to the child, so it then can jump directly to the child. But what is parsing and what is hard parsing exactly? Well, luckily, fetal or active session history, there's licensing involved with fetal or active session history, but got these flags. So that's really convenient. So I created this little SQL statement, which I can execute against a single SID. And then I just use GDB to break on functions, and then I'm going to look into active session history, whether the flag is set to indicate that it's in parsing. So that way, if the parsing is defined correctly in active session history, there's no guarantee. So I hope that the team who created hash is setting the flags correctly, but I have no reason to believe that isn't the case. So I'm breaking on these functions. These are the functions which I think should be somewhere on the border of parsing and not parsing. So I execute the warm-up SQL, which is select 1 from dual, and then I execute select 8 from dual, but I don't press enter. Then I log on to Oracle SysDBA. I obtain the PID, and it's TS. So TS is not the one with the star. So that's 9647. I attach to GDB using 9647. I source the breaks, essentially. These are just breaks and seed functions. And I'm looking at the hash state for the SID. Now, it says no row selection selected. If something is considered idle, it will not be stored in the S buffer, so you will see nothing. Then I execute, I press enter for select 8 from dual, and a breakpoint is triggered. And I'm then looking in hash, and it has all ends. So KPO AL8 is not part of parsing, as far as I know. So I go until KKS parse cursor, and then in par, which is in parse, says why. So the function before KKS parse cursor, because it's breaking on entering the function, is probably considered parsing, which is OPI OSQ0, whatever it might mean. I've done this for all the individual steps. I put breaks in and then gone through them. And I tried looking what is in parse and what is considered in hard parse. So obtaining SQL statement, that must be parsed. Inspection the session cursor cache, that must be parsed. Actually, what I thought was that as soon as for a statement, the database needs, your session needs to allocate memory for the handle, it would be hard parsing. But what I found is, until the initialization of the child cursor, anything is just considered in parse by the database. And it's only upon doing my research, if it starts doing stuff with a child handle, if it starts creating the child handle for you, that is, according to my research, so don't take my word for it, but that's what I see. Creating the child is hard parsing and nothing else. And the more I say it, the more it makes sense. But there is not a single thread of documentation that I know which actually says this. But my research says that creating the child cursor is hard parsing. So, I talked you through this whole process and these objects, so now that we are aware of this principle, things are not that simple, sadly. There are a lot of optimizations in Oracle. I was doing some testing, and look, it's in parse, it's in hard parse. Well, we saw that hard parsing is part of parsing, right? But it's also in SQL execution. And how the hell can something be parsing, but also already be executing at the same time? That's rather weird. So I took the backtrace, and this is really overwhelming. I understand. But if you look at the first one, at number 42, well, that's a coincidence. It says KKS parse cursor, so it is actually parsing. But then, if you look at KKS full type check, the type check is validating the child and potentially doing the semantic checking, because that's what OPI-SEM is. But if you and RPI-SWU2 means it switches. That it means it starts doing something recursively. And if you look there, you see RPISWU2 again, and at the top, you see OPI exit. So what is going on here is, it is parsing, but in order to obtain information for the parsing, it needs to execute some SQL to obtain that information. So it's actually doing a recursive SQL to obtain something because it's busy parsing and it needs extra data. So that's OPI exit. So that's what is happening here. Now that we know that, things might not be that simple, sadly. Because I thought I understood what was going on. So I thought if I break on a function which sits in between parsing and execution, and the parsing needs to create this information for me because otherwise I can't execute. So I must be able to execute, to obtain the execution plan. So I look at my session, I've got a SQL ID, and this is a statement, and I do a select from dual. No problem. Now I've got a different SQL, I look up the SQL ID which starts with 4R and ends on HH, and I try to look it up, and it isn't there, whilst I'm in between parsing and execution. What is going on? Well, first test is, I stopped on a breakpoint, I continue it, it continues okay, so the statement is okay, and now all of a sudden the plan is available. What is going on? I've just thought I understand what is going on, and now it's different. Let's break on the functions and look at the backtrace. And this is still is daunting. This is PRS CMD, so that's parsing. And I see KKS parse cursor, so we're in parsing, totally where we expected. And there's KKS parse child cursor, so the child cursor is created. This is as expected. This is OPI SEM. OPI SEM is the master function for the semantic checking. It's already executing. So the reason that I couldn't obtain my execution plan is, it wasn't there. It just did the syntax checking, and then it moved on to the execution phase. And in execution, it did the last part of the parsing, which is OPI SEM, and also APA DRV. So actually doing the costing, etc., and creating the execution plan. So it deferred it to execution time. And if you look at the flags in Edge, and this is quite sad, you see the exact same flags as you saw with the recursive SQL. So if you see these three flags in parse, in hard parse and SQL being set, you can't know, based upon these flags, whether it's recursive SQL executing or it is actually deferred parsing going on, which is deferred until execution time. You can't tell. And this is even more sad. I looked at $3 session time model, which is often really helpful in understanding if you have a parse problem or an execution problem. My hard parse, and what I did is, I put on a function on OPI SEM, I put a break function and I put a sleep of 1 second. So then 1 second it stops for 1 second in the semantic checking. And then looked at where the time is going. Well, I do it in OPI SEM, so, and that's hard parsing. So hard parse time elapsed is 1 second, right? That's logical, right? Because hard parsing is always considered parsing, the parse time is also 1 second. But because it is deferred parsing and it's done in SQL on execution time, SQL execute elapsed time is 1 second too. But the overall time I've spent is also 1 second. So if you believed what I, up until before this research, I thought was the case, if you thought that you could just say, okay, we've got parse time and execution time, and I look where the time goes, well, you can't tell, because it can be an execution time actually or not. You can't tell. So and I understand why this is, because you can bind your bind variable, and then it needs to understand whether the execution plan still makes sense. And you can do that after you've parsed. But your stats. To be honest, I think that the people who created this didn't realize this was going on, or it's a totally different team, and they made it with the best intentions. But now it's rather hairy. If you have a problem, well, I'm basically now told you that you have even less clue than you thought you had. So that's not really helpful. There is SQL trace, and SQL trace, because it's linear, right? After parsing, your line is written. So the parse line has the correct timing. This is also the 1 second sleep. So the parse line has the correct timing in, because that's the time spent. It writes the line, and then it moves on to execution time, and the time truly is done there. So this is where SQL tracing actually helps, by the nature of how it works. Contention scenarios. Library cache objects, as I tried explaining, are all protected by mutexes. There is documentation about library cache ledgers, and there are even fields in the data dictionary which still say library cache ledge. As far as I know, they don't exist. And if you look in $, $ledge children, and $ledge parent, you will not find anything related to library cache. So I think the entire library cache is protected by ledgers. And they are basically, they perform exactly the same function as ledgers. Mutexes perform exactly the same function, which is concurrency control. They have an added value. They also function as counter, so you can see how much time things are touched. And they are, the aim from Oracle is that these mutexes are simpler. Despite that, they have these states. And this is how in GDB you can look up the states. The ones which you probably will see if you start working with them is SHRD, shared, and EXCL, which is exclusive. So that's a shared mutex will get an exclusive mutex like log, and long exclusive. Here is this picture again. Hopefully you now have an idea and an understanding what this means, because some of my colleagues thought this was then quite daunting. I made a slight transformation. If you have contention on hash buckets, you have, at least in 18, you have a library cache hash bucket, but what I see is that after the hash bucket wait, there is a second mutex get for the hash bucket, which is simply library cache mutex x. And I obtain these by having 2 sessions, and 1 session I'm breaking on releasing the ledge, and then executing the exact same SQL, and then go function by function, each distinct function to see where it is. And I think this is really helpful because, well, it's not really helpful that library cache mutex x can mean the hash bucket, but also the parent or the child handle, because that is what I see being library cache mutex x. The dependency mutex x is working with the dependencies. That is when when a session tries to insert itself in a dependency list in a child handle. And what is interesting, the cursor mutex and cursor pin related waits are always because of the heap 0, are not the handle. So, and if you recall from what I said earlier, if you're having your SQL execution in the session cursor cache, it will go directly to the child. So, in that way, you can stop getting to some of these addresses, because it can jump to the child immediately. So, I think I said this earlier, as soon as there needs to be something changed in the handle, in the hash bucket, or in heap 0, it must make sure that nobody else is touching it, and it will take a mutex for that. So that is what a mutex does. And that is for every individual library cache object. And as you've seen, an hard parse touches and creates a lot of objects. So that's a lot of mutexes obtained. This is why it's fundamentally important that a session can do its work, because if you start doing this stuff, if you've obtained such a library cache mutex, you should do your work really fast and then release it, because other people will, other sessions will wait for it. And in some sessions, people already luckily said that using the database resource manager, and if only just to set it to the number of threads you have, should be mandatory for the database. And this is why. If you set it to just the number of threads you have, so it will never over allocate CPU, you're making sure that you do not leave the decision whether to stop a session or not to the operating system scheduler, which has no concept of consistency functions in Oracle, so it could push you off the CPU whilst holding a mutex, because if that happens, especially if it's a bucket mutex, it can have quite significant consequences. Your whole database can just stop functioning. And I've broken on the C function. I've seen this happening, that I just had to start because I couldn't even look in the data dictionary. So it can have really devastating impact. So it's fundamentally important that your CPU is never overloaded. You should use the database resource manager. If a session is creating a child and another session is trying to use that child, then obviously it must wait for it to be ready. That's kind of logical, right? You can't work on half an object. And what I actually did is, I once again gone through this list, stopped on the functions, and then executed in a different session and tried to see if I gotten a concurrency issue. Of course, if I break in the middle of a mutex, I will stop on that mutex. So it's not a mutex, it's just generating the hash function, etc. Much to my surprise, up until this point, outside of mutexes, up until searching compatible child, I could break at any time during the generation outside of mutexes, and the second function would just do the work. So there is no concurrency problem there, much to my surprise, really. This tiny bit, I think the $bill object is there and was traditionally used to lock a library cache object. So in these two occasions, you get the wait event library cache lock. After the CU enqueue is obtained and before the child is created, you get a wait which I've never seen in real life. I must be honest, I've never seen it, which is KKS FBC child completion. It more or less makes sense because we need a child and it hasn't been created yet, and then essentially all the work for creating a child cursor is protected by cursor pin X, wait on X. Remember, this is the wait event of a second session whilst performing the creation of the child. But I think this has changed when the mutexes came, because before this, I think it was library cache pin or library cache load lock or something like that. But that's what I remember from the Oracle 7, Oracle 8 days. But now it's cursor pin S, wait on X. I have some time, I think. Is that correct? Because there is one very important thing which I think everybody should know. If you execute something after your first execution, parsing is actually not the first thing that happens. And this is really much, well, it was kind of an eye-opener, but parsing is not the first thing that happens. Actually, the first thing that happens, well, actually what happens from your last execution, the library cache object that you've used is still locked. And if you look in $$ session cache cursor, $$ open cursor, you will see your last execution as being open, and it will remain open until you execute something new. And as you start executing a second SQL, the first thing it does, it stops the log. And if there are any allocations because of the previous execution, it will deallocate it once you start executing, doing something new. And so it's kept open. So you might see freeing resources. And actually, I haven't seen any issues with this, but actually there is, in cursor close, is a flag in active session history. And that is actually covered using in cursor close. You can get around this, but you can't do it in SQL as far as I know. You can, and this is how to pass a statement once and then fill the bind variables and continuously execute. And this is how you do it in Java, and this is how you do it in PLSQL. I'm not aware that you can do this in SQL. I think that's simply non-existent. Then, well, probably it should be the one. Yeah, it should be the last thing. After execution, the cursor is in Vlor open cursor is open, and you can see it because the log mode is n. N means null, and the heap 0 of the parent has the flag p, which means pinned, and that's obvious because there is a child, and because the pointer to the child is in the heap 0 of the parent. It must be kept pinned, which means that it can't be deallocated, because otherwise you would lose the child. And the child, if it's executed, the heap 0 is pinned. And what I found quite remarkable, but this is documented in a white paper which John Breckenridge and Connie Green, I think, wrote. Heap 0, which contains your child cursor information, which contains your execution plan, which is how you execute stuff, is not pinned. It can be flushed at any time. And if this is flushed, then, and this is a pointer which you might see, you're executing something, you're doing soft passes all the time, then all of a sudden you do a hard pass whilst nothing changed. Well, it can be because your heap 6, so your SQL A object is flushed by another session. Of course, it's kept pinned when you are actually executing. It can't rip the floor underneath your feet. It can't do that. But as soon as you stop executing and doing something with it, the pin is freed. And if a cursor is completely idle, then the log mode is 0, all the heaps are 0, so they can all be just moved away. So there is a lot of stuff, there is a lot of stuff in the shared pool which can be freed at demand, which you thought you had. That's essentially what I'm trying to say here. So this is when it became cached. If it's cached using session cache cursors, that's good, right? That is, then you have good and you don't do hard passes. But still, heap 6 is not pinned. So even if it's in the session cursor cache, it's not definitive. If it's active, it must be pinned, obviously, and a hard pass has pin mode X. That's the purpose of this slide. And I think I'll leave it to that. Are there any questions? Yes?
I think it's great work.
Thank you.
Presentation.
Thank you.
You said that during the execution new query, some work related to the old one needs to be done and maybe because for the old query listed in the same session.
Yes.
Is that correct?
Yeah. Yeah. So if you're executing something, then memory areas might be allocated, and some of them, I'm not sure, I didn't look really deep into that, but some of them are freed immediately after your SQL is executed, but some of them remain kept. And then only when you execute a new SQL and it sees that your new SQL is not, does not need it, it will free at that time.
Yeah, so that means that old query executed in the same session, not related in any way to the new one, can somehow affect performance of the new query. What do you think about this? Because to be honest, that's very surprising.
I think if it's, the question is if these memory areas kept open and kept for a previous execution, could that influence performance? I think, but I didn't look, I didn't investigate that part. I looked at a parsing, but I think this is really important information to realize is that it's happening, because even if it's session, even if your cursor is cached, it will end the SQL, even if it's 100% the same SQL, hash the value and then find, oh, it's in the session cursor cache, and it executes it again. It doesn't re-execute because it's the same. But your question is, these resources which are kept, could that influence performance? I think Oracle did a great job. I don't see any direct reason that that would take place. However, if you have just a gazillion connections, it will take an enormous amount of memory, despite the fact that these connections do not do anything. Having a huge amount of connections is actually a really a burden for the database in the sense of memory kept already. But I don't see any reason that this delayed clean out, if you like to call it that way, has any serious impact. I think really huge allocations which can be freed will be freed at will, because otherwise it would be silly.
Yeah.
So,
Okay, thank you very much.
okay. Well, I'm over my time, so if you've got any questions, and I can fully understand that you also need to think about it, what you just saw probably. I worked on it for half a year, so I don't expect you to fully understand it in 45 minutes. But if you have any questions, please come to me and I'll try to answer them as good as I can. Thank you.